Hello everyone, today we'll be walking you through our soft color segmentation pipeline and explaining how it efficiently implements the approach proposed in the paper Unmixing-Based Soft Color Segmentation for Image Manipulation by Yagiz Eksoy and his colleagues. At a high level, soft color segmentation is a method used to decompose an image into multiple layers, where each layer is defined by a homogeneous color and an associated alpha mask. These layers enable intuitive and powerful image editing operations such as recoloring, object isolation, or stylized blending. The first step in our pipeline is estimating the color model for the input image. This is done by analyzing the image's color structure and assigning votes at each pixel. Each vote is weighted based on two key factors: local color energy, which is how well a pixel's color is already represented, and image gradient magnitude, which helps us to avoid selecting edges as representative colors. Pixels with low gradients and poorly represented colors are favored based on this voting mechanism. We select seed points that represent the dominant colors in the image. Importantly, while the original paper uses Mahalanobis distance to compare pixel colors, we instead use Euclidean distance for its computational simplicity and practical efficiency. Despite this simplification, the results remain visually and numerically comparable. Once we have the seed colors, the initial alpha masks, we perform joint optimizations of per pixel alpha values and color layers using a sparse unmixing strategy powered by the Adam optimizer. This step minimizes a loss function composed of three terms: the data term, which encourages the reconstructed image to match the input image; sparsity term, which pushes each pixel to belong predominantly to one layer, which improves clarity and editability; constraint terms, ensuring the alpha values for each pixel sums to 1 and the image reconstruction constraint is closely satisfied. We also incorporate Lagrange multipliers and an increasing penalty coefficient using an ADMM-like approach, progressively enforcing these constraints more strictly during training. After each iteration, alpha values are clamped between 0 and 1 and then normalized per pixel.
Next, we apply matte regularization to clean and refine the alpha masks. This is achieved by using a guided filter, a fast edge-aware smoothing filter that uses the original image to guide where to blur and where to preserve edges. This regularization step smooths noise masks, especially in flat regions, preserves boundaries such as object edges, and ensures consistency in alpha blending by normalizing the masks again. In the final step, we further refine both alpha masks and layer colors using another joint optimization. This again uses the Adam optimizer, now focused on improving the pixel-wise match between the reconstructed and original image while keeping alpha values close to earlier refined ones. This step combines a reconstruction error term, a penalty for deviating from prior alpha masks, and a reconstruction constraint enforced via Lagrange multipliers and penalty terms. With each iteration, alpha masks and colors become more accurate and spatially coherent, leading to better final decompositions. Our pipeline improves upon the original paper in several key ways. We use Euclidean distance instead of Mahalanobis distance, significantly reducing computational time while maintaining quality. We adopt Adam-based optimization for smoother and more adaptive convergence. Our guided filtering and sparse alpha initialization steps are carefully designed for efficiency and scalability. By explicitly enforcing sparsity, we achieve cleaner, more interpretable alpha layers. In summary, our pipeline faithfully implements the ideas of soft color segmentation while streamlining key components for practical, efficient use. It produces clean decompositions, is easy to parallelize, and retains high visual fidelity across a wide range of images. Thank you for your attention.